Hello, everyone. Welcome to our first mathematical biology seminar of this semester. Today, we are pleased to have Professor Ricardo Cortez at Tulane University. He will share with us his research on computational models of self-propelled organisms. Let's welcome him.
Thank you very much. And so let me just start right away. Let's see. So what I really want to do today is just give you some idea of the methods and the applications that we've been looking at for the last maybe 20 years or so. And some of the methods are from back then, and some are some new versions and some modifications. So here's some motivation for what we do. So what we want to do is develop computational models that can capture interactions between thin filaments and some fluid around it. And usually these will be microscopic scale. So for example, in microorganisms, we might want to do individual or collective motions, and we want to be able to model flagella and cilia. For example, look at sperm motility or bacterial motion. And obviously the fluid environment is an important part of this. So there at the bottom, I have some questions that motivate the work. Sometimes we want to ask, are things, for example, the flagella or some microorganisms, are they designed to optimize something? Or many times the flagella have, for example, several functions, so it's not clear that they would be optimizing one of them specifically. But we look at these questions. Here are some photographs of things that we have in mind. So on the left is a bacterium with a lot of flagella coming off different parts of the cell body. And in the middle, there's some photographs of bull sperm in this case. So in each frame, in each panel, you see two photographs that are taken just slightly at a different time. And so you can see the symmetry and the beat on the left, and then some asymmetries and different beat forms, depending on some chemistry going on or some hyperactivation and things like that. And on the right side, I have, well, there's a lot of work now being done on artificial swimmers. And so there's the designs of these guys are, there's a wide variety of them, and the idea is that they might want to go through environments that are not necessarily uniform, just a fluid, but maybe they have filaments in it or polymers or things like that they have to make their way through. And so there's more and more technology every year, and there's also experimental work that is based on new technology that is able to make these things smaller and smaller. So we want to look at what can be done. By the way, if you have any questions along the way, you can feel free to interrupt me or to put it in the chat or whatever you want. But it would be great if you want to ask a question. All right, so here's a little movie of a particular bacterium. It's this guy has only one flagellum, so it's nice to study. And you can see that the flagellum is helical, so they just kind of corkscrew their way around the fluid, and then they go around in circles, sometimes depending on the environment around them. There could be this is in a microscope, so there could be a flat, a glass plate underneath or something that is affecting the motion. And sometimes they also stop rotating their flagellum, which makes a recoil in some way, and then that reorients them, and they go in a different direction. The other thing that is going to become important for us is that many of these organisms, for example, the case of sperm, they have to make their way through regions like this. For example, this ZP is a extracellular matrix. So it's a filamentous thing. It's like a network of filaments and polymers and other things. And there's also chemistry usually that happens when the sperm reaches it. But the point is that it's a different region, it's a different environment within that region than it was outside. So typically we would want to be able to model something that is in a fluid, for example, in a viscous fluid, and then entering and exiting a region that is viscoelastic in some ways, for example. So more of this to come in the presentation. And so for me, I think the challenges have to do with some of these things that I have listed here. First of all, it would be great if we have some kind of model of how the forces develop along the flagella, for example, or along the organisms, and how these forces result in some kind of beating motion that produces swimming, so that we're not putting in a particular swimming motion necessarily, but we're putting in some way of developing forces. This is not always possible, or sometimes an initial step in the simulations would be to just prescribe a motion. But what we would like in the end, if possible, is to have the motion be an emergent part of the model. Yeah.
Ricardo, I just had one question. I'm guessing you'll talk more about this later, but for this ZP,
yeah,
is the right way to think of this as essentially an obstacle to the sperm that they have to overcome, or is it more of something that is helping the sperm to essentially fertilize the oocyte, or some combination of the two?
Yeah, my understanding is that in this case, when a sperm makes it to the ZP, then it triggers a reaction, a biochemical reaction. And because for one thing, I think part of that is that it makes it possible for that particular sperm to fertilize the egg and not have a bunch of other ones also do the same thing. But mechanically, right, it's a different environment. And so I'm going to focus more on the fluid dynamics and the swimming through this region, but there would be a lot of biochemistry also that has to happen.
Great, thanks.
Okay, all right, I think this is fine. So let's look at some of the ingredients for the model. So in a simplified version, I guess, right, we need a model for the forces that develop along the flagella or the cell body. We need a model for the fluid motion, the viscous fluid around it, the environment, and how the motion is generated by the forces. And there will be some elasticity or some the flagella will be flexible, and so there's a geometry involved in how this is affected by the fluid motion and how this all feedbacks, right? So when the geometry changes, typically the forces will change, and because forces might be connected to curvature, for example, or things like that. And so new forces develop that creates different fluid motion, and the fluid moves the organism and that's the feedback mechanism. So I'm going to show you a quick little animation that was not done by me. It was one of the students that I work with, but this is just to show you that these are exactly the same. Let's see. They're the same shapes, but what the only difference between those two is the stiffness constant. So what this is a flagellum is a helix, and it's been created out of springs and points connected. So there's a little, like a little tube with a lot of springs and points, and in one case the stiffnesses of the springs were computed in a way that optimizes the swimming speed. And in the other case, they were just set to a fixed constant. And you can see how different the simulations are. So these are the kinds of challenges that we face, setting parameters, values, for example, for stiffnesses of springs and things like that. But let me talk about some of the elements that are common to most of these problems. In general, we can think of this as some kind of flexible surface, maybe, or a curve, depending on how you're modeling things, that pushes the fluid around, and then the fluid moves and affects the shape of the organism, which develops new forces, and that couples the two. So the starting point for us is usually the Navier-Stokes equation. Well, this is quickly going to be reduced to a linear equation, the Stokes equation, but typically the Navier-Stokes is the starting point with external forcing, and the external forcing is the organism, external to the fluid. So I'm sure you have seen all of this. So here in the equations, P was the pressure, U is the fluid velocity vector, external force is F, viscosity mu, which is considered constant for us at the moment, and density. And so depending on the characteristic length and speeds in the problem that you're doing, after dimensionalization, there's only one parameter, one dimensionless parameter that pops up, which is the Reynolds number. And that Reynolds number is defined here. And this is a nice little diagram from Purcell's paper. So a person swimming might have a Reynolds number of 10,000 or so. Some fish might be about 100. And then microorganisms would be roughly about in this range, 10 to the minus 3, 4, 5, something like that. So most people say this is close enough to 0 and set the Reynolds number to 0 and reduce the equations to just the Stokes equations, which are now linear and in between U and F. Okay, so this is going to be the model equation: incompressible fluid and viscous flow. So there's lots of ways of solving these equations. People use immersed boundary methods or other things. I'm going to show you the method of regularized Stokeslets, which is based on the fundamental solution of this equation. So I'm going to consider a point force for the fundamental solution, and this is the incompressibility condition. So the quick derivation would be to take a divergence of the Stokes equations, and the divergence of U is 0, so that leads to an equation for the pressure. And if I define G, this Green's function, to be such that the Laplacian is the delta function, I can write the pressure this way. And once I have the pressure, I can put it back into the original equation and solve for the velocity. And this is the well-known formula for which is called the Stokeslet. And most, well, one thing to notice is that this is singular, as it typically happens with fundamental solutions, but the singularity is 1 over r. and this is the Stokeslet.
I have a very naive question.
Yeah.
So I see people use different methods to calculate fluids. When is the time to use this Stokeslet?
Well, if you're modeling the fluid motion with the Stokes equations,
Uh-huh.
so if you made the determination that the Reynolds number is small enough to be considered zero,
Right.
then you're working with the Stokes equations, and at that point, the Stokeslet is a fundamental solution to this equation.
So whenever you're using Stokes equation, you use Stokeslet?
You can use Stokeslet.
Right, right. But I guess there are other methods too.
Well, so the Stokeslet is because it's a linear equation, you can find this fundamental solution, and
Right.
then if you have forces distributed over the surface, for example, then the flow they generate is the integral of that. That becomes the kernel in your integral times, and this is an integral over the surface.
Mm-hmm.
So this is a representation of the solution of the Stokes equations in terms of the forces, the surface forces. But you could discretize the differential equation itself, right? You could take the Stokes equation and just put a grid or something like that, like finite differences and things like that. So you can discretize this differential equation. That would be a different method for solving this. So
Yeah, thank you.
I'm just going to use the fundamental solutions. And so this is the kernel, the Stokeslet. And the thing to notice is that it depends when this R is the distance from the evaluation point to the points where the forces are. So
Right.
if you're evaluating the flow far away from the surface, the singularity doesn't bother you. This is smooth and there's no problem. If you want to evaluate at a point where it's very close to the surface, then there will be points on the surface where this distance is very tiny. And that's usually called a near singular integral. And one has to be a little careful computing that accurately. And if the evaluation point is actually on the surface, then there will be a singularity in this integral, but it's something that it's a weak singularity, so it can be integrated. So surfaces are not typically problematic. However, sometimes we want to model maybe a flagellum. We want to model not as a surface, but maybe as a curve. And then if you have forces along a curve like this, now the integral is a line integral over the curve. And now the integral diverges because this is a 1 over r singularity over a line integral that gives you a log singularity. And maybe the worst case scenario is if you have just scattered points with forces. So this would not be a flagellum, but if you had point forces scattered around, then there's no integration here. All you can say is that the velocity would be the superposition of all the velocities from each force. And this would be undefined at the points where the forces are applied because there's a singularity there. So one has to deal with the singularities. And what we did some time ago was to think about it in the following way. We thought about it as saying, well, the singularity comes from using the delta function in the derivation of the fundamental solution. So what we thought about doing is to replace the delta function with a smooth function, maybe like a Gaussian or something like that, or some other function that is concentrated near zero, but is smooth. And here are some properties. So I'm going to use radially symmetric functions. But then you can solve, for example, if you solve the singular version of this is just Laplace's equation. The solution is the Green's function like this. This is the same singularity. But if I use a regularized delta function here, my solution will be smooth because this is a smooth function, and so the Laplacian, if the Laplacian is a smooth function, the function is smooth. And so what we have is a different model, basically, is what we have something that doesn't have it removes the singularities. So the idea is going to be to rederive the Stokeslet fundamental solution, but with one of these functions here. And we do exactly the same derivation. You take the divergence, and that gives you an equation for the pressure. And here I have to define a regularized type of Green's function, which satisfies this equation, and then another function B, which is like a biharmonic equation function. And with those, I can find the formula for the what we call the regularized Stokeslet. And so these will look like a Stokeslet far away from the force, but at the point of the force is now finite, and there are no singularities. So that was the idea. I guess this has been more than 20 years ago now for regularized Stokeslet. And for the rest of this talk, I'm going to go back a couple of slides. I'm going to use this particular function. And if I derive my formula for that regularization, I get this. This is my kernel for the regularized Stokeslets. And notice that if you were to take the limit as epsilon goes to 0, you go back to the original singular version. Yes.
I wanted to ask about that. So how should we think about epsilon, for example, in one of these applications you mentioned? Do we think of it as a numerical parameter that you want to essentially do some convergence study and take it to 0? Or do we think of it as having some physical meaning?
Yeah, I would like to think of it as having physical meaning. So in other words, it's not just a numerical parameter that you want to take to 0. In particular, if you're modeling a flagellum by a curve, taking epsilon to 0 is not going to converge to anything. You would have to do something different. So I want to think of it as these don't have compact support, what I just showed you, but if you think about the function having compact support, that means there's a little sphere where the forces are distributed. And so it's like a cloud. For me, it's like a cloud of forces rather than being point forces. If you think about at every point here, there's a little sphere where the forces are distributed smoothly, then it is you might think of it as the radius of your flagellum, for example. So the forces are concentrated within the flagellum. And this will come up in a second. So I'll show you what the consequences of that is. But for now, this gives us a way of computing the flows due to whether the forces come from surfaces or curves or scattered points, the same formula applies. And so here's some further comments about this. These are exact solutions for this particular type of forcing. So there's no approximation really. It's just the model of the force that is different. How the spread of the force depends on this epsilon, and in the sense of distributions, this function phi approaches the delta function as epsilon goes to 0, and this will come up too. For example, this particular way of looking at the relationship between U and the force, you can think of, this can be inverted. So for example, if I have a particular velocity that I want my flagellum to have, and I know this velocity, I can try to find the forces that produce that velocity by setting this up as a matrix, a linear system. Okay. And then finally, so I'm going to skip some things, but traditionally, if U and P are the solutions to Stokes equations like this without forcing, then it's easy to see here that if you differentiate this equation with respect to almost anything, if you take a derivative with respect to x, for example, the dp dx and the du dx will also be a solution of the same equation. And so you can differentiate further and get more solutions. And these are the different, this is like a multiple expansion of the Stokeslet. And the same thing you can do with the regularized versions. So here's a regularized couple of elements. Okay, let's see. I'm not going to say too much at the moment for the forces, but I need to figure out a way of computing my forces. So if I have a filament like this, and I think of it as a bunch of points connected by springs, then I can compute the forces based on the tension between the, if these springs have a resting length, then there's always a tension here. So those are tensile forces, and then I might want it to have a specific curvature at different points, and that also creates a force. And if I have a model for computing forces like that, then I can then use my regularized Stokeslet to tell me what the velocity is anywhere I want it. So okay, I think
Sorry, Ricardo, maybe let me just ask you to repeat the last thing you said, because it went a little quickly for me. So I understand by using the Stokeslet or any of these multiple versions of it, once you know the force, you have basically an exact formula for the velocity. But I think what I didn't quite catch, where is there a linear system that needs to be solved? And also, how do you define those forces?
okay, let me see. There's two different issues here. So if I have a regularized Stokeslet, which comes from my Stokes equation with a particular forcing term here, I can differentiate this. For example, if I take the curl of this equation, I'm going to get something like the solution from imposing a torque, right? And that's, so the derivatives, the curl of these P and U will become the pressure and the velocity corresponding to an applied torque rather than an applied force. So for instance, those are these guys. So here's the Rotlet, which is the solution for a torque. This is a potential dipole, which is the Laplacian of the Stokeslets. But the other thing that happens is that, let's see, maybe I have it here. So if I have to have a model for the forces, so if I have a flagellum, for example, I might have some way of computing my forces like Peskin does in his fibers or something like that. And so if I have a way of computing forces along the flagellum, then I can find the velocity at any point. But what if I have it the other way around? What if I say I I've observed this, the motion is in a certain way, and so I would like my points to have a prescribed velocity. And I need to find what forces can produce that velocity at all the points. So this, if I set up this linear for every point on my flagellum, I set up this equation, I end up with a linear system like this. All the velocities are related to all the forces. And this is what I would have to invert, this matrix, to find the forces that will produce the velocity I'm prescribing. And this depends on the geometry and what you're doing. For example, if you had a sphere, well, this matrix could have a null space, a non-trivial null space, because sometimes, like in the case of a sphere, if you just push on it normal to the sphere with equal forces, nothing moves because it's incompressible, right? So that gives you that's the null space in that case. But for open curves like flagella and stuff like that, I don't think there's a null space. So this typically is invertible, and we do that. Does that answer some?
Definitely. And then, so I think now I understand, and maybe the next slide you were showing in a particular case that this system can be inverted, and you can even write down what the forces should be.
I'm not sure I can write it down analytically what the forces are, but I can set up the matrix and invert it.
Got it. Thank you.
So here's the first example. So if we think of a bacterium, for example, with a helical flagellar bundle, and so I'm going to ignore the cell body for the moment and just have a model for the tail. This is not just a curve. This is a little structure, like a little tube that has, on the surface of the tube, there are points, and the points are connected by springs. And the way we produce the motion is that we put a torque in front of it to rotate it. So we're rotating the first cross section here, and that by the stiffness of the springs, it's going to start rotating the whole thing. And I think we also have further out in front. So it's known that when you have a helical flagellum that rotates in one particular direction, the cell body counter rotates in order to conserve, to have zero net torque. And so we have this torque here to start rotating it like a motor would rotate the flagellum, but then we put a counter torque out in front to represent the cell body rotating in the other direction, and to have a zero net torque in the end. So these are two different simulations. One is in open space. So this is, if you look at the left side, this is, you can see these dots maybe is where the counter torque is, and the torque is right at the first cross section. So it's rotating the helix, and the helix is, if it's stiff enough, then it's going to maintain its shape more or less. And then when it interacts with the fluid, it just swims, I guess. It translates itself. But we also wanted to know what happens if you have a confined space. So this is the same helix, but it's stuck in a tube that has got a pretty small radius. So it cannot turn around, it cannot go backwards. All it can do is move forward. And it moves faster than in open space when you have this confinement. And so we wanted to look at some more of this. And we started looking at the stiffness of the springs that connect the points on the surface of the flagellum. This is hard to see, but let's see, the stiffness decreases from top to bottom. And the x-axis gives you the Rutledge strength. This is the how much torque is being put at the front. And this is the average distance traveled per revolution. So what we see is all these different curves depending on what the stiffnesses of the springs are. The top curve, which is more or less a constant line, is when the stiffnesses are infinite. So this would be a rigid helix. If you have a rigid helix rotating, then you get this constant distance per revolution. And it turns out that there's this number, this sometimes called a sperm number, and it's related to all these dimensions. There's the rotation frequency that we put into the helix, the length of the helix, the radius of the helix, the viscosity of the fluid, and some bending rigidity. So this can be interpreted. The sperm number to the fourth is this expression. You can interpret it in different ways. It could be a ratio of time scales, or it could be a ratio of force magnitudes. But in terms of the sperm number, all of these curves collapse onto a line. So it's this is a good way to look at these guys. So we wanted to look at what happened with if the confinement was different. So this is the same organism, but the tubes are getting smaller in size, in radius, from bottom to top. The top one is the smallest tube. And if everything else is the same, the one in the smaller radius tube swims the fastest. So confinement enhances the swimming in a way. As you get confined more and more, somehow that is helpful to propel yourself. And then we did a couple more experiments. In this case, what you see here is the same organism in different tube radius, and we're not letting it move forward. So we're keeping it from translating, just to see the motion. And on the left side, so let me see. On the left side, well, you just see what they're doing. And then on the right side, these are coming straight at you. So we're looking straight down the tube. And I'm wondering if you can notice what's happening with these guys as they rotate. If you see the difference between the left and the right, for example. So if you had a good eye, what you saw was that for the smallest radius tube, the nose of that spiral, the helix, spirals inward. And then for the largest tube radius, the nose of the helix spirals outward. In fact, it ends up hitting the wall at some point and crashing. And then the one in the middle just simply rotates in a circle, so there's a particular radius tube that makes the swimmer just kind of roll, but not spiral out or in. And so because this spirals in for the smaller tube, we understand this to mean that if the tube is sufficiently narrow, then the flagellum will align with the tube axis because it spirals in to the center of the tube. So we thought that was an interesting result that we hadn't anticipated. Okay, I'm gonna switch a little bit. Let's see, what time am I supposed to end? I have maybe 15 minutes, 10 minutes?
Yes.
Okay, so what this was related to the question that Thomas asked.
Sorry, Ricardo, I just wanted to interrupt. I see there's a question in the Q&A.
Oh, okay.
Guess is asking what sets the constraint for how small the radius of the tube can be in the simulations?
Oh, the amplitude of the helix, right? So the helix has a certain amplitude at the back, and the tube, it has to fit in there, otherwise nothing else. Yeah, but otherwise it would just hit it.
And I guess I also had a somewhat related question. How are you implementing the tube? Do you need to compute a different Stokeslet in the confined case?
Yeah,
or
we are putting a bunch of Stokeslets on the surface of the tube and solving that linear system that we talked about to make sure that the combination of all the velocities produced at the tube wall is zero.
And so in that case, it's kind of a mixed type equation, because you have some of these material points where you're prescribing velocity and other ones where the velocity is free.
That's right. So we have forces along the helix, and that produces a velocity not only on the helix, but it produces a velocity on the tube walls. And then we have to compute forces on the tube walls to cancel that velocity there. And now we have forces on the tube and the organism, and that produces the total motion.
I see. Thanks.
I also had a question. How do
Yeah.
you decide how many points you place on the wall or on the flagella?
Yeah, well, on the wall, you have to try to model this as a solid wall, right? So the more points you have, the better, but then your linear system becomes really large.
Right.
So this is not a very good answer, but it's going to be as many as you can handle in the linear
I
system.
see.
So sometimes, in fact, we just have a chunk of the tube, and then we move it as the helix moves, we move it with it, so that we don't have to have a big tube. In terms of the points along the flagellum, that's what I wanted to talk about now. So maybe what happens is that this is one way to think about it. Suppose you have a function represented by this dotted line. And I want to, that's like my force, and I want to represent it by the superposition of a bunch of forces with these functions. So I've drawn here two consecutive, so think of this as basis functions. So I have a grid, this is like my flagellum, I have a bunch of points, and at each point I have this function, and I have a neighboring function. And somehow the sum of all of these guys have to, I want to approximate this dotted red curve. So if these are too narrow and not close enough, then they start wiggling like this. The approximation is not so good. If I make them too fat, then the function is smooth, but it misses the corners and things like that. So a good choice is somewhere in between, where you can capture the force. So you need this blob, these are called blobs, these functions. You need them to overlap enough to give you a smooth approximation, but not too much, right? So it typically ends up being similar to the separation between points in the flagellum. Like if you have a point separation of h, the epsilon is roughly around the same value. So E of epsilon over delta S would be 1, something like that. But this is a problem because based on what we talked about earlier, if I want to define my epsilon to be based on a physical parameter, so for example, if I want my epsilon to represent the radius of this flagellum, I would have to say my epsilon is this small. And if I need to make my discretization of the flagellum about the same as epsilon, then that's going to lead me to have to use 400 points or maybe 500 points along my flagellum just to be able to use epsilon this small. And this is overkill, right? This doesn't require that many points. So I'm going to skip ahead a little bit, but what we did more recently is called the regularized Stokeslet segments. What we think of it is, we think of the flagellum as piecewise linear pieces, so like a polygon, straight pieces. And in each straight piece, the force is not just a constant, but it's a linear function from one end to the other. So maybe this is better. So here's a segment of my flagellum, and I have a force here and a force here, and I'm assuming that the forces along in the middle is a linear function. So I need to integrate to compute the velocity at any point due to this one segment of my flagellum. I need to integrate my regularized Stokeslet when the force is a linear function, and this is the position that's related to this linear function here too. And it turns out that these integrals one can do exactly. So this is the same thing. They're based on having to integrate. If you think about this as a linear function of alpha, linear function, this will be a cubic function of alpha. So we need alpha to the 0, 1, 2, and 3 powers divided by r to either r to the first power or r cubed. So it turns out that these integrals you can do exactly, and so you can compute the solution to this. There's a recursion here, so I'm going to skip ahead, but excuse me. The main idea is that if you think about the flagellum as piecewise linear pieces, and in each piece the force is linear, you can compute the exact solution, the exact velocity due to that. And this gives us the main point of this is that now I can compute with, for example, epsilon being 1 over 300, and I only need 24 segments to represent my flagellum, and I can do the computation. Whereas before, so this essentially has decoupled the epsilon and the and the point separation in my discretization. So this is just an example of a simulation where the bead is more or less planar, and every so often there's a random perturbation to the motion so that it goes in different directions. But this is just a proof of concept. So this is the take-home message is that with these segments, I can use a very tiny epsilon, which is now on the order of the flagellum radius, and my points in the discretization of my organism doesn't have to be connected to that. Okay, I'm wondering if I should stop or give you the last little bit here.
I think it would be great to hear it. At least I'd love to hear it. I mean, some people may need to go in a few minutes. One thing we could do is maybe just pause and see if people have questions
Sure.
on what you've done so far, and then for those who can stay, we can continue.
Okay.
Okay, so I think we can just go ahead.
So our motivation here is that there are these environments where these networks of filaments and polymers and things that are where the gap size in between here is more or less on the same order as the
Sorry, Ricardo. So
there is a question.
there is a question after all. So how do you simulate the turns in the simulation?
Yeah, the turns in the simulation. I actually put in at random points, random moments in time. I add a random torque at the front of the where the dot is, and that basically rotates the organism in a random direction, and I only do it for at particular times. This
I
is,
also,
yeah,
oh,
go
sorry.
ahead. No, go ahead.
Well, I also wanted to ask, so when you said that in this kind of segments method, you're assuming that the forces are linear.
Mhm.
So I kind of understand maybe if the segments are linear, but could you just explain a bit more what you mean by linear forces?
In each segment, my force goes from being a value here to this value.
Oh, I see. Okay.
In between, yeah, it's just a linear function of the parameter along this segment.
Okay, thanks.
And that's not you can do something else. I mean, you can make it quadratic or cubic. That doesn't affect, that just affects the numerators here, which are computed from a recursion, so that's okay. Making the shape piecewise linear is the key here.
And for this recursion to be solvable, is it important that there's some like ordering on the segments, the force is different at the leading segment, or
No,
does it not matter?
No, the velocity is got these terms, and each term is defined this way, and the recursion, there's an order to the recursion here, but you need all of these t's to compute the velocity. And the ones that have the zero in the front, those are the ones you compute analytically. So you have to compute two of them analytically. We have expressions for them. And the rest follow from the recursion. So.
Okay, thanks.
Yeah, the final little bit is this network. So what we think of it is a little chunk of the fluid that is viscoelastic, let's say, but it's not proper to use a continuum model of the viscoelastic fluid, because this is the gaps are of the same size as the organism head, for example, as the cell body. So it really is important to have a discrete version of this. And our model is something maybe a little bit abstract, but it's like a cloud of points. I think of it as a cloud of points, and some of them are connected to each other to produce the elasticity. So imagine these are connections by springs. And so when an organism goes through this region here, it's going to move the points, and it's going to stretch those springs, and those springs are going to then produce some force that is going to hold them together. So that all together produces the effect of having an elastic, a viscoelastic chunk of of fluid here, or a region embedded in a viscous fluid. So maybe this makes more sense. So here's a little cube of that type, and all of these are points connected by springs, but I don't think of the springs as being material pieces that are obstructions to the motion. They're just there to produce the elasticity, produce force that are mimicking elasticity. And in fact, they're not just Hookean springs, they're Maxwell elements. So it's a spring and a dashpot combination. So that if you stretch this element, the dashpot opens up and it eventually the resting length changes. So we mimic that by, so this is like a Hookean force for the spring. But the length of the spring, the resting length, also changes as you stretch it. So I'm just gonna end with a simulation. I think this is the idea here. This is work. This is really recent work. We have an organism is going to be a helical tail, but this is not a curve. It's a little tube like this in a spherical cell body. They're all discretized, and it's going to make its way through some network of springs and these Maxwell elements. And so depending on the parameters that we choose for the springs, this is the stiffness of the spring. This is a moderate stiffness. Eta equals infinity means that it's just a Hookean spring. So the organism makes its way through that. If we decrease eta, now there's viscoelastic behavior, and so there's deformation here. And if I make this parameter smaller, this becomes very stretchy, and the organism drags a lot of the points with it. I don't know if this is really making any sense, but basically the two parameters, the E, this is the stiffness of the springs, and this eta is something related to the dashpot parameter. That gives you different behaviors of the viscoelastic chunk of material. And so we're looking into how to use this, and how to model when the organism itself could change the properties of the material as it goes through. So I'm just going to stop here because I'm running out of time. So thank you very much.
Thank you so much for that exciting talk. Do you have any more questions? I have a quick question from the perspective of a biologist.
Yeah.
Do you collaborate with biologists to actually measure those parameters or test your simulation results?
Yes, we do. Sometimes to measure the parameters, sometimes to tell us something about what the motions they observe. So we have two collaborative projects at the moment. One has to do with choanoflagellates and how they move their flagella for feeding purposes, for example, and what flows they generate when they form colonies and things like that. And another project has to do with sperm of insect sperm, which are really wild. They're really long, and they do very complicated things. But as a matter of fact, we were just talking to them this morning, to our collaborators, to see if they can measure the stiffnesses of the sperm along the length. I'm not sure that they can do it, but maybe they can.
Also, it's a very abstract question, but when you think about biological systems, can you do more than prediction? Like, what is the common way to give the perspective, perturbation to the system? You know what I mean?
I am not sure I understand.
Because in biology, you want to do more than observation to study the system. You want to give a lot of perturbations and see if you can predict all the perturbations, the output of the perturbations accurately. So what are the common things you can
Yes.
do to the system?
So my hope is that using simulations, we would be able to perturb the system in various ways. And then if we observe something interesting, then give that information to the biologist and say, well, when we perturb it in this way, we see something interesting. Can you check to see if you observe the same thing or not?
Right. What kind of perturbations do you usually do?
Well, what kind of perturbations? We can do all kinds of things, right? We can make the flagella shorter or longer, or we can make the cell bodies disappear. We can do yeah, the proportions. I mean, I don't know. We can also change the fluid properties and see, but I'm not sure that we're at that point at the moment yet. We're still in a way validating what we're doing with measurements.
All right, thank you.
I also had one more question, kind of going back to something we were talking about earlier, whether this epsilon in the regularized Stokeslet method can be interpreted in some physical way. How easy would it be to change the shape of that regularized Stokeslet kernel? I'm just thinking about the flagellum modeled as a tube, and right now the kernel you use is kind of peaked at the origin. But if it's more like a tube, then I guess it might be peaked a bit away from the origin on the surface of the tube. Is that something that is straightforward to do, or would that require a lot of?
No, but the center of the function is always where the force is, right? So you at the location of the force, that's where the center of the function is.
But I guess you could imagine. I think you could imagine a version of this function that's, say, bimodal, peaked a little bit away from where the point is.
I see.
So you put, I mean, almost like I'm imagining basically the derivative of this function, more, well, maybe not the derivative, because I'm thinking of something that is strictly non-negative.
Okay, but I understand what you mean.
I'm wondering, is that something that, how hard-coded is the specific shape of phi and what you're doing? If you played around with that a little bit and just, consider different models of the structure, how easy would that be?
Yeah, I think you can. That's not a big problem. I think you can do that. The only thing you would have to be able to do is this derivation, basically, which is given the function, solve for this g, and given g, solve for this b, because the b is what you need for writing out the formula. So this just requires, since it's, in my case, they're radially symmetric, so these are ODEs, really, they're not PDEs. So I think as long as you can do the integration and get these functions, then you're in business.
Got it. Yeah, okay, that's interesting.
I never thought about making it bimodal like that.
Well, yeah, because I mean, I guess if you have like a hollow tube, in my mind,
I see. So
guess,
you're thinking of putting it at the center line.
yeah, I'm thinking of putting it, which I guess you're avoiding that because you're putting all of the force points on the surface.
On the surface, right?
I see. Okay, I see.
But
yeah,
But it makes sense. What you're saying makes sense. If you put them on the center line, then you want it to peak at the surface. Interesting.
Okay, if we don't have any more questions, let's thank Ricardo again.
Thank you, guys.
Yeah, thank you so much.
Thank you.
Sorry, I was a little bit over ambitious with the presentation.
Oh,
It was
no,
a
not
little-
at all. Not at all. This was great.
Yeah, I enjoyed so much. Thank you.
Thank you, and stay in touch if I can help you in some way with regularized Stokeslets. I'll be happy to.
That would be really great.
Sure.
Yeah, I know Kana is working on them right now. So
Yeah, struggling a lot.
Oh, well, if I can help you, let me know.
Thank you.
Okay.
Okay.
All right.
Okay, thank
See
you
you
so
later.
much, Ricardo,
Thank
and
you. Talk to you soon.
talk to you soon.